So hi everyone. Thank you all very much for coming here. My name is Heng. I work on Google Research and Machine Intelligence. And today I'm very happy to have the opportunity to tell you about Sibyl, about Google scale machine learning. And I'm going to borrow the next 15 minutes of your life, and I'll do my best to make sure it's worth it. If not, please call Google customer service. So, there's this one quote that is my all-time favorite, and that is, any sufficiently advanced technology is indistinguishable from magic. And when we think about machine learning at Google, we think about making magical moments happen for billions and billions of users around the world. And speaking of users, let's introduce one of our users, Chris. So Chris is a young professional stylist with mustache, software engineer. He loves traveling and shooting on the road. Also loves watching sports, but not so good at playing them. So one day, Chris, hopped on the last-minute flight to Russia. But unfortunately, Chris loves traveling, but not so good at learning new languages. So Chris knew nothing about Russian. Fortunately, he's got his phone and with Google Translate installed. And just, open up his viewfinder and instantly Google used machine learning to both recognize the text from the image through image processing and then do machine translation in real time. So he's happy to read like attention, wicked thought, but thought still worse, whatever that means. He's happy now he can read signs without knowing another language. Then, while he's enjoying his trip, he got an email from his coworker. He's like, "Oh, really? A work-related email when I was traveling?" So his teammates is looking for documentation, and he's really not in the mood for replying emails. But luckily, Google has this smart replies on Inbox, where it processes the incoming emails and use recurrent neural networks to generate recommended replies. Like, we can choose from one of the three. So Chris selects, I'll have to look for it, and instantly send and continue his travel. So you can think that if we continue down on this path, then someday you don't have to be with your advisor anymore. Your inbox and your advisor's inbox just start talking to each other without any intervention from you. So, isn't that sweet? And after Chris go back to the hotel, open up his laptop, and only to find that not only were all his photos backed up to Google Photos, but Google Photos automatically recognize all the objects and scenes from years of travel he's been to. So, like all the basketball games and baseball games he's been to, his favorite beers. There's this one night, it was at nightclub. He insists he didn't remember, but Google Photos remember. Another magical moment happened for Chris in Google Photos. Now, when Chris returned from his trip, there's this, just a lazy Sunday afternoon, he turned on YouTube and found this Trojan Power video. And so Chris is really pumped by the way, Chris is also a USC alum. You can see I'm trying to blend in here. Only to find that all the videos on the right recommended for him are all the ones he loved. So he just keeps watching and watching, enjoying his time on YouTube. And Chris thought that, hey, if these machine learning algorithms are so magical, why don't I start programming one myself? And he remembered that a few weeks ago, Google just released TensorFlow. And TensorFlow is a general purpose framework, a data flow framework that is for general numerical computations, especially for all kinds of machine learning algorithms. So you can take your data, use these primitive building blocks to build all kinds of algorithms, and it takes care of computing gradients, updating the model parameters, and once you write the graph, it can be deployed on several different platforms from CPUs to GPUs and even mobile devices. So Chris very happy, and he thought to himself, like, now I can build any models. Why would I need Google? I can just build my own YouTube video recommenders from this. But what Chris didn't know is that it takes much more than model productionize machine learning. So the ideal world that Chris was thinking is that you have an input watch video from the user, and you just need to train a machine learning model, and then you apply prediction to all the videos you have, and then you can find the top ones to show on the output. But the real world is much messier and ugly even. So from the input audio, first you have to log them. And there's all these giant logs, and you have to do sectionalization right and join all these huge tables. And then after some data processing, you need to do feature transformation. Get features you need. You need to do model training, model exporting to export it to a format that your server can serve within tens of milliseconds, which is usual requirement for an online service. And not done yet, because there are billions of videos just in the YouTube corpus. So you cannot just score billions of videos within 10 milliseconds. It's basically computationally feasible. So you actually have to do some indexing and then retrieval when the query comes in. Then finally, you can serve the output to the user. But luckily, our team built Sibyl at Google. So ideally, the real world returns to the much simpler ideal world, or at least almost, with Sibyl. So what is Sibyl? Sibyl is a large-scale machine learning service that is widely used across Google. So initially, from the beginning, it was designed for Google's largest data set. And by largest, we usually means that it's on the order of hundreds of billions of training examples. Can train models with about 1 billion weights and explore a feature space of 1 trillion. And it's widely used in production in almost every product area. So probably the products you've been using, there's Sibyl inside of it. And it's end-to-end system, continuously ingest new data and export to different serving systems, easy to use and easy to understand. So product teams have config system set up. We have full pipeline management, and they have monitoring, a web UI to monitor the health of their models. Sibyl is built on a set of solid machine learning foundation that supports a wide variety of machine learning models. This includes logistic regression, linear regression, long-tail Poisson regression, supports factorization machines and embedding models. You can do multi-class classifications, or you can do learning to rank for ranking problems. It's fast, scalable, theoretically sound, and learning rate free algorithms, meaning that they're guaranteed to converge, and you don't have to set the learning rate yourself. And we also, internally, we also provide support and training and education. So the way we work is we will engage with the product teams, and we provide, dev on call support, or we provide machine learning consulting for them. And we also have rotation programs, so they can come to the machine learning team, do a joint project with us, and launch machine learning enabled products in their product area. So that's an overview of Sibyl. Now let's first look at what kind of problems that Sibyl is mainly solving. So if we think about it, many Google problems are essentially search ranking problems. What we mean by that is they're usually a query from the user side, and we need to return a ranked list of documents. And when I say query and documents, it can mean many different things. So a query can be a search string, a web page, user's history, or any other context, like time and location, and so on. And documents can also be a variety of things like apps, movies, songs, images, and so on. So when Google receives the query from the user, first we need to do a retrieval, to select relevant candidates from the corpus, usually on the order of 1 billion candidates, and reduce that candidate set to about 100 documents, which is manageable by the ranking algorithms. And then we apply ranking to return the list of ranked documents. So how does Sibyl fit in here? So when a user issues a query and receives a ranked list of documents, the user can perform certain actions. The actions can be clicking on the link, watching a video, purchasing a product or app, or engaging with the app, and so on. So all of these queries and documents and user actions are recorded in Google's logs. So Sibyl takes these logs as input and then train on these data and outputs a model. And then the model is used for ranking. And how do we actually rank the document is we rank the documents by query.scores. The query.score is a prediction of some user actions you want to optimize for. So for example, you want replays, you want video watches, you want more user engagement, user happiness, whatever you want. Then you will fix the query and make a prediction for every single document in the candidate set. And finally, you have to rank the result. So in short, Sibyl learns models from logs, ranks the candidate documents by the predicted query and doc scores, which then maximizes target user actions. So that's the main types of problems that we're solving and we'll talk about today. Of course, there are others. But then let's also talk about what kind of scale we're looking at and the sparsity structure. So when we say Google scale, usually means you look at the sample by features matrix, where each row is an example, and each column is a feature. Then usually number of sample is on the order of 100 billion to trillion, and the number of features is in the billions. So in training, usually need to finish in hours or less than a day. So about sparsity, most of these features are categorical, meaning, for example, if it's country, then if there are 200 countries, for any given example, only one of them will be active and the other will not be active. So this is also known as one-hot encoding, you guys are familiar with. Or if it's continuous feature, usually it's discretized, like if it's user age, we will have different buckets for different age groups, and then they become binary features, one-hot encoding. So for any given example, usually only hundreds of them are active out of this billion feature space. And many data sets at Google actually have these properties. So when we think about machine learning solutions, we usually have these properties in mind. Okay, so that describes the problem we're solving, structure of the data. Now let's look at a running example of how do we do apps recommendation for Chris. If Chris visits Google Play Store on his Android phone, how do we do recommendations? So there are usually two important ways you can do recommendations. The first one is if we know that Chris installed Priceline, and we can go back to the historical data. For people who downloaded Priceline, many of them also downloaded Kayak and Expedia, maybe because they wanted to compare prices when they're booking their flights and hotels. So this kind of recommendation is called memorization, and that is based on frequent co-occurrence of items. That means these two things happened together in the past, and they're strongly correlated with the positive label. Then the model will learn that this is a good thing to show this. So it's more explicit and topical because it's really happened in the past. So the results will be more directly related with the items that the user already had. The other important types of recommendation is, we call it generalization. And generalization is really based on the transitivity of similarity. That means if A is similar to B and B is similar to C, then A is also similar to C. So for example, we know Chris installed Priceline, and we also learned that people who are interested in traveling also interested in exploring new cuisines and new restaurants. So Yelp might be a good recommendation. Or if people who install Priceline has a business trip coming up, and then they need a transportation app like Uber. So Uber might also be a good recommendation. So these kind of things you can recommend even if they didn't co-occur in the past. That's more, it might be more subtle, but it's also more diverse in the sense that it can help users to explore more different apps in the App Store. So these are kind of the two main goals we want to achieve in a recommendation problem. And recommendation is also a search ranking problem, like we discussed. First place where the query is the user, the user features and the documents you want to show, for example, will be the apps. So now let's look at how do we use Sibyl to train a machine learned model to tackle this problem. So we can frame the problem as that given that Chris just installed Priceline, if we show Kayak as an impression, what would be the likelihood of install? Okay. So the simplest model you can use is a linear model. And a linear model, you can start adding features to it. For example, the first feature we add is a user feature. The user, Chris, just installed Priceline. And an impression feature, the Kayak app you're about to show. And importantly, there's a cross feature being added. Cross feature is a combination of the user feature and impression feature, meaning having installed Priceline and seeing Kayak as an impression. So it captures the and relationship of these two binary features. And by adding these cross features, we can achieve memorization that we wanted in the first place. So it can achieve by adding these cross features to capture the co-occurrence. However, so how we actually learn this model is, for example, the user feature. Knowing that a user installed Priceline doesn't give you much information about how likely the user will install any app in the next round, right? So you may get only a 0.1 weight. Since Kayak is quite a popular app, you may receive a 0.5 app being very quickly or highly likely to be installed impression. And then there's this cross feature for users who have installed Priceline and seeing Kayak as an impression. There's a high likelihood of an install, so you might receive a 1.4 weight. And then, of course, you add this weight up together, passing through a sigmoid logistic function, and then you can convert this weight to probability, and maybe the probability of install is 88%. So you can achieve memorization through this, but you can you probably noticed that the feature that we added was very specific. So if the user didn't install Priceline, or if the impression app wasn't Kayak, then this rule doesn't apply anymore. So if you want to do more generalization in your prediction, this can be achieved by adding more general features like app category or user demographics and so on. For example, we can add more general cross features, being having installed a travel app and seeing a travel app category as a recommendation. So this way you can generalize your learning to new travel apps in the future. And usually say that these human-defined features and cross features are more understandable and controllable for the product. So imagine that if some users suddenly report that they see a bad recommendation result or search result, then you can actually go into the model, look at what features you added and what went wrong, and then you'll be able to fix that or remove that. To have more understandability and controllability. But the problem is that, as we talked about, the feature space is very wide and very sparse. So if you add a cross feature, then most of these user impression pairs did not happen in the training data. So most of them are unobserved previously. So how do we actually generalize to unseen user impression pairs without the burden of manual feature engineering? You can add more features, but there are probably some features that human cannot imagine, or even domain expert cannot specify in the first place. So that's why Sibyl also supports factorized embedding models, or also known as the factorization machines, initially by Sanford Randall, who's also now at Google. So factorized embedding models are like this. So you have the user features and impression features as the base features. But instead of creating a cross feature that captures the end relationship between them, between this specific pair, you learn a dense embedding vector for each of the user feature and each of the impression features. So you can think of these dense embedding vectors like dense floating point encodings of the features or some high-level concepts, and they are randomly initialized. And as you go through the data, you learn you have the prediction compared with your target, you have your losses, then you backpropagate that to adjust your embedding values such that you can better predict the labels in your training data. So in the end, prediction time, you can take the dot product similarity of these two embeddings. So if these two items are similar, their dot product will be higher, and otherwise it will be lower. So if you use this kind of factorized embedding models, we can now generalize the predictions previously unseen user and impression pairs, because you're not explicitly memorizing a certain combination. And you can think of embeddings are like features, but they are automatically learned by the algorithms, not specified by humans. Of course, you can go deeper and train deep neural networks. And in fact, that's a natural extension from the factorized embedding models, factorization machines. The idea is that given sparse input features, you can also convert them into dense embedding space, and then go through several hidden layers, where each layer is really just a linear combination of the previous outputs, and then passing through some activation units. And then with that, you can now learn more complex interactions between user and impression embeddings, rather than just a simple dot product similarity. But also notice that as you move away from the human-defined or feature-engineered cross features, your model is now less controllable and understandable, meaning that if you show a bad result, you probably have no idea at which stage it went wrong, and it will be harder to fix because you don't directly control the meaning of each dimension of the embedding. Okay. So memorization and generalization both are very important for Google and I guess for any general products that want to serve recommendation results. So we also one area we're actively working on is also combining these two, right? Combining a large, very large but sparse linear models with memorization through cross features, and also through like factorized models or neural networks with embeddings, such that you can generalize to unseen user impression pairs. So the other way to look at these is just from another perspective. Is you train a linear model. Essentially, if you look at the query feature by document feature matrix, where each row is a query feature and each column is a document features, so both of them are maybe on the order of millions to billions. In linear model with cross features, you're learning a weight for each of the row column combinations. You look up the weight of that in the intersection. Whereas in the factorized embedding model, you're essentially factorizing this huge weight matrix you had to learn into two smaller matrices, where one is the query by m queries by k dimension embeddings, the other is a k dimension embeddings by n documents, where the k is usually much smaller than m or n, usually on the order of 100. So now you're kind of compressing this information, like using much smaller matrices and being able to reconstruct the original weight matrix, and thus you're able to generalize more. So if you use embedding models and you represent every app, or more generally every document in an embedding space, you also embed your users in the same embedding space, then you can think of recommendation problem is just like finding the nearest neighbors, finding the nearest document that's closest to the user. As you can see that as you get more and more apps in the embedding space gets crowded, and it's also likely that two apps will be close together in the embedding space, but not so related to each other. So basically, as you do more generalization, you pay the trade-off of less memorization or controllability. So that's some lessons we learned through modeling and while we're solving real product problems in recommendations. But we also mentioned that machine learning service is much more than a model and a learning algorithm. Right? We talked about this in the beginning. So let's talk about something else. Let's talk about infrastructure. And as John Oliver said, infrastructure is not sexy, but it's a very important problem. So lots of people like to talk about modeling and learning algorithms, but infrastructure is really important and makes all of these possible. So let's look at Sibyl and from 10,000 years, right? So obviously this is still simplified because we have limited time and I don't want to get sued. So from the user side, we want to make it as ideal as possible. We want the user to see the ideal world that we described in the first place. So they just give us our training samples, and then we see a server model that they can plug into their server and start, generating revenue or making user happy. So the first stage of Sibyl is feature selector. Feature selector is responsible for doing the mapping from features in the logs to integer encodings. Okay? So basically, it assigns integer ID to each of the unique features in the data set, of course, filtering out less frequent items and so on. And each feature family, or called columns, has its own dense integer space. For example, the country might have its integer space, domain name or publisher identity or something like that. They all have their own dense embedding space. And they are variable length encoded, so in this decreasing frequency. So we're able to save space and make computation much faster. And then the second job, the training data generator, then translate each examples in the original log form to the new integer-based and also column-oriented compressed feature representations. So then the learner take these column-oriented and compressed training data and then trains the model with distributed gradient descent and many of its variants. There are many learning algorithms you can do that. And each of the learners, since the data is now column-oriented, so each of the learners will be relevant columns. Like, for example, if in this model you want to explore this feature 1, 2, 5, you only need to load these 3 features without parsing the rest of the logs. So it parses much less data and more efficient. And also, since it's column-oriented, we can easily transform features, like taking 2 columns and do the AND relationship with the cross feature we described earlier. Okay. And also, each learner keeps the snapshot of the model and all the sufficient statistics in memory. And the benefit is that memory lookups are much faster than remote procedure calls or RPCs. So this is opposed to other alternative designs like parameter servers, where you store all of your parameters in servers, you do lookups and updates through internet. So this allows the learner to do much faster lookups and updates. And since we did that dense integer-based compressed training data, and the integer is in the dense space, so the models can be stored in a dense array rather than a hash table. So that means it's more compact, and the lookup is even faster. And finally, as we go through each iteration of the models, every once in a while, the models are checkpointed in Google's distributed file system. We keep all the files versioned, and the downstream jobs can always use the latest version, or if there's any errors or anomalies, you can always go back to the previous version. Okay. And then the model exporter takes a checkpointed model and converts it into one of the many servable output formats. So as you can imagine, with so many different products, they have so many different serving systems. So we have a job to help them convert it into the servable formats such that it can be served in, say, 10 milliseconds or less. And on top of that, we have a experiment browser that is a web UI for monitoring pipeline progress, health, or any data anomaly in your incoming data. And that's also a very important thing that you want to be aware of. And one of the attributes of this pipeline is that we use a distributed file system for computation and to drive the computation. So these jobs don't talk to each other directly. So they're always running and looking for the upstream outputs of the previous jobs. And then once there are new files, new directories, they'll start ingesting the outputs from the previous stage, and then it starts processing. And all files are versioned, so it handles incoming and always changing. So a little more on a very high level, how we do distributed gradient descent on MapReduce. I'm sure that this is familiar for many of you. Basically, you have an objective. you want to find the weights, the optimal weights that minimize your loss functions. Maybe that's a squared loss, log loss, or ranking loss, depending on your problem. So there are two main stages. One is you want to compute the gradient, and then you want to update the model parameters. The first stage is easily parallelizable across examples, and the second stage is easily parallelizable across features. So if you visualize it, we have, again, n examples and d-dimensional features, and then the mapper, will take some blocks of the example and start computing the sufficient statistics for each features, and then finally the reducer will receive all the updates for the certain model parameters, and then do the updates. And also, to be able to run very fast and to be able to handle the largest data sets that we talked about, it's also highly optimized for multi-core map reduce. So we do use multi-shard combiners. It's like within every core you have the median reducers, right? And then that's aggregated across multi-core. So the output is much smaller than if you didn't use that. And we also share models and also the stats across multiple cores, so you can amortize the large memory usage. And the result of that is obviously it will be very fast. It's processing 2 million features per core per second. And I think this is somewhat outdated. I'm pretty sure right now it's even faster. And since we made all kinds of optimization in data representation and I/O, it's actually not I/O bound and it's CPU bound.
Did you use this?
So Sibyl use batch iterative learner, not stochastic gradient descent. But there are also, so this is the main one we use, but we're also using other variants, the stochastic learning algorithms. Okay. So of course, there are other essential parts of Sibyl we couldn't cover today. For example, like data anomaly detection, feature transformations, how to do continuous training and serving, training serving skew detection. For example, if you in the training, you represent country as uppercase and in serving it's lowercase, and suddenly all the model doesn't apply. Or we have model analysis tools for the product teams, and you can do online A/B testing tools and dashboards. For you to test your machine learning algorithms on products. Okay. So a quick summary. What we talked about today is just sharing with you. There's Sibyl, it's a large-scale end-to-end machine learning service at Google. It's widely used across many product areas. We share with you the lessons on memorization plus generalization, how they are both important for you to do recommendations for users, and also we covered some of the optimization that makes it scalable and highly optimized distributed system. And of course, there are a lot of exciting, ongoing, and future directions. So here are just a few, if you're interested. We're building 100 times better learner, or at least trying to, for the largest data set at Google. It's bigger than the ones we described earlier. We're looking at new optimization algorithms, like, for example, SDCA, stochastic dual coordinate descent. One of them. There are many other optimization algorithms that we're always interested in looking, either from the academia or from the industry. And obviously, there are a lot of focus on deep neural networks. You can probably see from Google's publications or products, and also sequence predictions using LSTM, so on. And you're also very interested in doing so-called non-myopic predictions, as opposed to like doing a static prediction on the next, what is the next best thing to do. Instead, we should optimize for a long-term reward or some objective that we want. So reinforcement learning is also one thing that we're actively looking into. So then I want to thank all the Sibyl teammates. Since we're an alphabet company, we're starting all of them from A to Z. You can see that we're still missing B and E. So calling in for Brian, for any people who are interested in joining us here. Also, special thanks to all the contributors and partner teams at Google Research and Machine Intelligence and other product teams. So, last but not least, we are actively hiring. So, if you're interested in working on machine learning, or if you have a strong background, if you're very passionate about machine learning, we're very happy if you can join us and drive the future of machine learning at Google and through the world. So, there are a lot of opportunities, like including internship. I think, I assume some of you may have already applied. If so, you can feel free to talk to me, shoot me an email, and I can help you forward to our teams. Or if you're graduating, we're also actively hiring full-time software engineers and research scientists. There are a lot of exciting research problems and also industry's best practices we can work on and learn. So if there are any questions, please feel free to send email to me at hengtze@google.com. So, looking forward to you being part of the future with us. Thank you very much.